Hi class! In this video we're going to talk about graphing our rational expressions. So this is lesson 2.7 in unit 2. So first, grab some tea. I've got Bengal spice. And let's get started. Okay, so here we have a rational expression. So we are told to graph each of the following functions on the axis that is provided. So what I'm given is, in number 1, is this rational expression. It looks like I have a quadratic as my numerator and a linear on my denominator, right? So whenever I'm given a rational expression, the first thing I'm going to want to do is factor that. So we're going to factor our numerator. So I have x squared minus 4x minus 12. I'm looking for a product of negative 12 and a sum of negative 4. So I need two numbers that multiply to negative 12. And when I add them together, it's negative 4. So I can think of a few examples, and when I am thinking about this one in particular, I come up with negative 6 and positive 2. Because negative 6 times 2 is negative 12, and then negative 6 plus 2 is going to be negative 4. So my factored expression is x minus 6 times x plus 2 on top, and x plus 2 on the bottom. I can't really factor that any much more than that. So now I have an expression that is x minus 6 times x plus 2, and it's divided by x plus 2. So if you remember from our lesson on simplifying rational expressions, that means we can actually cancel out the expressions that are the same on the top with the ones that are the same on the bottom there, right? However, just because I'm canceling it out, that doesn't mean it's not going to play a part in our restriction. So if you remember, x cannot equal negative 2, right? So that is because if x were to equal negative 2, I would be having a rational expression where I'm dividing by 0, and that just can't happen. So I have that x can't equal negative 2 here, and we're going to look at what that means in a second. And I'm left with just y equals x minus 6 with a restriction of x cannot equal negative 2. So what does that look like? Well, y equals x minus 6. Well, this is a linear equation, right? And if you remember, in linear equations, they have the form y equals mx plus b, right? So here, my slope, my m, is 1. So I have a slope of 1. And my b, my y-intercept, is negative 6. So if you remember how to graph those linear equations, well, we start with our y-intercept. So my y-intercept is over here at 0, negative 6 on my graph, right? And I have a slope of just 1, so that means I'm going to go up 1 and over 1. And I can do that a few more times until I'm able to draw a line. Now, this is the case for pretty much all of my points except over here at x equals negative 2. So if you remember, x cannot equal negative 2 because in my original expression, that would cause me to divide by 0. So instead, what's going to happen is at negative 2, I'm going to get a hole. So I'm just going to write that in like an open circle, right? And then I can connect my line while ignoring that open circle. So my line looks something like that. So this is the line of the equation y equals x squared minus 4x minus 12 all over x plus 2. And here I have a hole at, looks like it's at negative 2 and negative 8. I cannot have I cannot have the point -2, -8 on this line. But all of the other points are fine, right? So here is my final graph of this expression. So that's all fine and dandy, but what if I can't factor my expression and simplify it to look like a line, like this one? So example number 2, I have a rational expression of x plus 2 over x minus 1. So just looking at this expression, the first thing I want to do is see if I can factor it. Well, I can't factor an x plus 2, and I cannot factor an x minus 1. So I have to come up with something else to do instead. So something else I could do is, well, I could play a little around a bit with my numbers and turn this rational expression into a reciprocal expression. So here's what I mean when I say that. So let's play around a bit. So let's say I wanted to cancel out something on the top with something on the bottom. So let's say I want to get an x minus 1 on the top. In order for this step to be equal to this step, I'd have to add 3 afterwards, right? Because x minus 1 plus 3 is the same as x plus 2. And all of this is going to be over x minus 1. All right, so far all I've done is turned a 2 into minus 1 plus 3. And I picked minus 1 because I have x minus 1 as my denominator, right? So once I have that, well, I can expand this a bit. I can break my fraction into x minus 1 over x minus 1 plus 3 over x minus 1. Right? So going from this step to this step, all I did was I just broke one expression into 2 expressions here, right? And since I know x minus 1 over x minus 1, that's just the same thing on the top as the bottom, that is equal to 1. So I have x minus 1 divided by x minus 1, that's equal to 1, plus 3 over x minus 1. So in Unit 1, we talked about how we can graph a function that has a parent function of 1 over x, right? So we talked about graphing f of x equals 1 over x. And we talked about transforming this parent function, right? So to turn this function into our new expression here, it looks like I have a horizontal translation of 1 to the right. So I have f of x minus 1. I have a vertical stretch of 3. So I'm multiplying it by 3. And a vertical translation of 1. Right? So this is the transformation that's happened to 1 over x in order to get this new expression 1 plus 3 over x minus 1. Right? So if you remember what our parent function 1 over x looks like, a quick way of remembering it is you can always create a table of values, right? So whenever you're in doubt, you can create a table of values. So let's just do that. So let's say I have an x and the expression 1 over x. So when x is negative 2, 1 over x is going to be negative 1/2. When x is negative 1, 1 over x is going to be negative 1. When x is 1, 1 over x is still going to be just 1. And when x is 2, 1 over x is going to be 1 over 2. So my original function has looks kind of like this. I can't have x equals 0 because I'd be dividing by 0. So there's going to be a vertical asymptote here, and I have 1 at 1, 1. When x is 2, I have 1 at 1/2. Similarly, if x were equal to 1/2, I have another point here at 2. And it kind of mirrors on the opposite side. I have a point at negative 1, 1. And then when x is negative 1/2, it goes to negative 2. When x is negative 2, it goes to negative 1/2. And I get this curve where my line is always trying to approach it's always trying to approach 0, but it's never going to quite reach 0. It's never going to reach the line y equals 0 here. I have a horizontal asymptote horizontally. It's never going to quite reach it. There's no number I can divide 1 by. Like I can't divide 1 by any number to get 0 in my y, right? So that means y is going to be infinitely getting smaller and smaller, but never quite reaching 0. And similarly, as I get closer and closer to an x of 0, I can't divide by 0, but I'm just going to get closer and closer to this, a very large number over here as x gets close to 0 from this side. And if x gets close to 0 from this side, from the negative side, it's also a very large number, getting larger and larger in the negative area, or technically getting smaller and smaller, right? But it's never going to actually cross that y-axis. It's never going to reach an x of 0. So this is what we call a vertical asymptote here. The asymptote means, of course, that we're getting closer and closer to the line without ever touching it. And here is our horizontal asymptote. So similarly, I'm going to have a vertical asymptote here, but it's not going to be at 0. It's going to be at x equals 1, right? So I can't have x equal positive 1 in my function here, because that means I would be dividing by 0, and that just can't happen. So right off the bat, I can draw in that new vertical asymptote. So this is my new vertical asymptote. X cannot equal 1, right? And I can see here that I have all of my, so what happened is I just moved my vertical asymptote 1 to the right, right? And similarly, I have this y asymptote over here. It's going to be moved 1 up, right? So if I have 1, if y equals 1 over here, it's always going to be either smaller than 1 or bigger than 1, but there's no number that I can divide here. Like 3 divided by any number is never going to equal 0. This expression right here is never going to equal 0. So that means that y is never really going to hit 1. So it's kind of like my horizontal asymptote was vertically translated up by 1. So I can similarly write that in over here. So I started with a vertical asymptote of 0. It was translated to the right by 1 over here. And I started with a horizontal asymptote of 0, and it got moved up vertically, right? Because I have a vertical translation here. So it got moved up vertically by 1, and now I have a horizontal asymptote of y cannot equal 1. All right, so what happens to the rest of my points? Well, they are also going to be moved over, right? So I have, let's take this point 1, 1, for example, right? So horizontally, it's going to be moved 1 to the right. So it's now going to appear at 2. And it's going to be multiplied by 3. So it's going to go up, multiplied by 3 turns into 3. And then it goes up by 1 again. So now I have a point at 2, 4 instead of 1, 1. So similarly, I have a point here at 2 and 1/2. So it's translated to the right by 1, and then multiplied by 3. So 1/2 is now 3/2, so it's over here, and then it's moved 1 up again. And over here, I'm at 2. It gets moved over to the right by 1. It's multiplied by 3. So 2 times 3 is now 6, and then 1 more. So now I have this curve that is approaching an x value of 1, but never quite reaches it. and it's approaching a y value of 1 but never quite reaches it. And I can do the same thing with my points over here. So here at -2, it's going to be moved to the right by 1, and then it's multiplied by 3. So now I'm at -3/2, which is over here. And then it's going to be added 1 after that. So now I'm at -1/2 again. And then this point, I've got -1, -1. It is moved to the right by 1. So multiplied by 3. So I'm over here at -3, and then added 1 afterwards. So that one's over here. And then over here, I'm at -1/2, -2. So it's moved to the right by 1. It is multiplied by 3, so it becomes -6, and then moved up by 1. So it's over here. All right, so here I have a line that kind of mirrors the other side, right? It's kind of like this one was mirrored over here. And it's approaching my asymptotes on both sides as well. So this red line that I've drawn is the graph of y equals x plus 2 over x minus 1. So let's kind of review a little bit about what happened. So here, in this example, in example 1, I canceled out my denominator, which caused a restriction. So when I canceled it out, I got a whole at -2, -8, right? So it appeared as a whole because it was canceled out. And then in this example, I couldn't cancel out my denominator, so I was left with a restriction in my final answer, and that restriction in my final answer appeared as a vertical asymptote, right? So here I have a summary in the next sheet over here. We have a summary of what do we do when we need to graph a rational expression. What do we need to do when we graph a rational expression? So first, we factor anything that's possible. Then we state any restrictions that apply, and then simplify, right? You don't want to forget any restrictions, so we should write down our restrictions before we simplify, just to make sure that we don't forget any possible restrictions, right? And then number 3, if a restriction is removed, right? So if you're able to remove a factor from the denominator, then we call those removable discontinuities. And if it's been removed, then that means it's going to result in a hole in the graph at that value of x, right? And if we have any factors that remain in the denominator, well, that is going to be appearing as a vertical asymptote, right? So if it's removed, it's a hole. If it stays, it's a vertical asymptote. And then we get to determine what the horizontal asymptotes are if they exist, and then we graph the remaining function. And don't forget the holes as well. All right, so let's do another example. So this one, it looks like we have a linear equation on the top and a quadratic equation on the bottom. So even if we were to cancel something out, it looks like we're going to be left with some sort of x on our bottom, right? So let's factor that quadratic equation on the denominator. So we have x plus 2. There's not much I can do with the numerator. But I have x squared minus x minus 6. So I need a product of -6 and a sum of -1. Right? Well, the two numbers that really jump out at me for that is -3 and +2. So I have x minus 3 times x plus 2. Well, lo and behold, it looks like I do have a factor that can be canceled from the top to the bottom. But as I'm doing that, let's not forget to actually write down those restrictions. So I have one restriction at x equals 3. X cannot equal 3. and x cannot equal negative 2 from here, right? So now I can go ahead and cancel that out. Since my restriction from the x plus 2 is being canceled out, it looks like this one's going to be a hole, and this one's remaining, so it's going to be a vertical asymptote. So I'll say that again. We have y equals 1 over x minus 3 as my simplified expression, and x cannot equal negative 2 or 3. So that means I have a hole at negative 2, and I have a vertical asymptote here at x equals 3. So let's find what that hole is. So let's find the hole. So when x equals negative 2, I have a hole, right? So that means I have a hole at 1 over negative 2, negative 3. So that's equal to 1 over negative 5. So I have a hole at the point negative 2 and negative 1 over 5. So I just plugged in my x value to find the y value that is corresponding to the hole at that x value, right? So this means my function cannot exist at this one point, right? And then also I have this vertical asymptote at x equals 3. So let's go ahead and draw that vertical asymptote on my graph. So I can't have x equals 3. Right? So x cannot equal 3. And when I look at my rational expression, there's no vertical translations up from the parent function of 1 over x. Or another way of putting that is that there is no number I could ever, like 1 over x minus 3 is never going to equal 0. I cannot divide this by anything in order to make this fraction equal 0, right? Although as I divide it by bigger and bigger numbers, it will eventually approach 0. And that is pretty much the definition of a horizontal asymptote, right? So that means I can't have a y of 0, right? So when it comes to plotting this, that means I'm going to have, my original point was at 1, 1. It's got moved over horizontally by 3. I have a horizontal translation of 3 to the right here. So I'm moving this over 3 to the right, and pretty much everything is just getting moved over 3 to the right. So I can kind of already guess what my other points are going to be looking like, right? So I have this plot over here where it's approaching an x value of 3 but never quite reaches it. And here it's approaching a y value of 0 but never quite reaches it. And then I have the same thing over on the other side. But something interesting happens here at x equals negative 2. And when x equals negative 2, I have a hole, right? So if you remember, I have that hole at negative 2 and negative 1/5. It's kind of hard to see on this graph, but we do still need to indicate a hole with an open circle. So I'm going to draw my line, but I'm going to make it really obvious that there's a hole right there and even indicate what that coordinate is of the hole. So what I'm looking for when you're working on graphs, so what I'm really wanting to see is, can you identify your vertical asymptote, right? Can you identify your vertical asymptote like this one? Can you identify your horizontal asymptote, which was over here? I'm going to mark it as HA, a horizontal asymptote. And can you indicate where the holes are, as well as the general shape of what that graph is going to look like? All right. Good luck, everyone. Your homework for tonight is a worksheet, which you can find on our class website under lesson 2.7. Let me know if you run into any problems, and we can take it up in class.